Welcome everyone. Welcome to the second Chandrasekhar lecture. Without any delay, let me welcome Professor Arul, who is our head of department, to say a few words about our department and the center. Arul.
Thank you very much, Chandra. Well, it's really a pleasure to be part of the second Chandrasekhar lecture this evening. Just to give you a brief background about the Department of Physics here at IIT Madras, we are one of the largest departments in the country today with over 55 faculty members. And we have a series of academic programs, which are from the undergraduate engineering physics right up to the doctoral program through standard master's and 5-year master programs. We have a vibrant programs here at IIT Madras, and with this large number of faculty, we have a diverse set of research interests. And I'm really proud that we count among us young and experienced at the same time a set of cosmologists and gravitational physicists. And not to boast, but well, maybe to boast as well, IIT Madras itself has been ranked for the third consecutive time as in the national rankings as a #1 institute and #2 in a research institutions category. And also we have a position of an institute of eminence as categorized by the government of India. And as a part of this, last year, there has been a significant amount of funding that has been put into several selected centers, formation of centers of excellence. And I'm happy to say that about 9 of these centers are originating in the Department of Physics. And one of that is the Center for Strings, Gravitation, and Cosmology. And they have been organizing the Chandrasekhar lectures, and this is the second of that, as well as they're organizing the school around which this lecture is based. So I'm really pleased that the center's activity is taking off in this manner, and for other centers, it shows us the way forward. So, on behalf of all the members of the Department of Physics, I welcome all of you, and I look forward to the lecture by Professor Cliff very much. It sounds really interesting, and I look forward to it. Chandra, Professor Cliff.
Thanks, Arul. Sorry, I was disconnected in between. I think the internet connection at my place was not very good. Yeah, there was a request in the chat, I guess, to clarify on Chandrasekhar lecture series. So we did start this series last year, and we expect to have four Chandrasekhar lectures every year. Many of you would know that Subramanian Chandrasekhar had its college education in Chennai. And in fact, we were surprised to learn that Professor Clifford was a postdoc fellow with Chandrasekhar in Chicago University. Anyways, maybe you would learn more about Chandrasekhar lecture series in our next notifications. But let me continue with introducing Professor Will here. Professor Clifford Will is a distinguished professor of physics at the University of Florida and an associated researcher at IFE Paris, He was born in Hamilton, Canada in 1946. He obtained a PhD in physics under Kip Thorne from Caltech in 1971 and was a Fermi postdoc fellow with Subramanian Chandrasekhar at University of Chicago. After 38 years on the faculties of Stanford University and Washington University in St. Louis, in 2012, he moved to the University of Florida. He is a member of the US National Academy of Sciences and a fellow of American Academy of Arts and Sciences. In 2019, he received the Albert Einstein Medal for Albert Einstein Society in Switzerland. And in 2021, he received the Einstein Prize of the American Physical Society. He has published over 220 scientific articles and 4 books. In 1986, popular book Was Einstein Right was selected one of the 200 best books for 1986 by the New York Times Book Review and has undergone translation into many languages such as French. His latest book is Einstein Still Right with Nicholas Eunice has been translated into Chinese and recorded as an audiobook. With further ado, I will welcome Professor Will to deliver the lecture. Professor Will.
Thank you. Well, it's a great honor and pleasure to be able to give this lecture, particularly since, as mentioned, I was a postdoc with Chandra at the University of Chicago way back in the day. One of the things I learned from Chandra was a deep appreciation for history. And so my talk today will be mainly a historical talk about the rebirth or renaissance of general relativity. In the popular imagination, there's a kind of fairy tale version of the story of general relativity that goes something like this. In 1905, as a lowly patent clerk, Einstein discovered special relativity. Then, after 10 years of hard work, in 1915, he found general relativity. 4 years after that, Eddington and colleagues measured the deflection of starlight in agreement with his predictions. Einstein's theory was triumphant, Einstein became very famous, and everyone lived happily ever after. Well, the real story of general relativity is much more complicated than that. At the time of Eddington's measurements, there was considerable skepticism, especially among American astronomers, of the correctness of his measurements. And indeed, within almost less than a decade, the whole subject of general relativity receded into the backwaters of science. It became very dormant and was not considered a fit subject for real scientists to pursue. And I'll describe a little bit of how that happened. But in the 1960s, there was the beginnings of a tremendous renaissance for general relativity. I'll describe some of that. And by the time I entered Caltech and joined Kip Thorne's group in the summer of 1969, this relativistic wave was building, and I was lucky enough to catch that wave at that time. And I'll say a little bit about my own personal experiences during the decade that followed. My main focus in this talk of a renaissance will be on experimental issues, and indeed, the final topic will be the synergy between theory and experiment in our field. Most fields of physics take this idea for granted, the synergy between theory and experiment. But in general relativity, this has been a new development and has been a big factor in this rebirth of general relativity. Now, this fairy tale really begins in during the year following the publication of general relativity and centers around Arthur Stanley Eddington, a leading astronomer of the day, as well as a theorist of great note, who in 1916 received from Willem de Sitter in Holland copies of Einstein's papers of November 1915, where he first presented general relativity. You must remember, this is in the middle of the First World War, and Germany was cut off from most scientific interactions with the outside world, except for neutral countries like Holland. Eddington immediately realized that this was an extraordinary new development in gravitational theory, and he prepared a detailed report on it for the London Physical Society. And with the British Astronomer Royal, Sir Frank Dyson, started planning an expedition to measure the deflection of starlight during a total solar eclipse. Again, the First World War was raging, and there was a danger that Eddington himself would be drafted into the army to help fight in the battles in the closing months of the war. But his exemption as a conscientious objector was finally upheld, and he did not have to go to war. A few months later, of course, November 11, the war ends, and early the next year, two teams departed England for Sobral and Principe. That solar eclipse of 1919, the path of the eclipse passed over northern Brazil, across the Atlantic, and then across Africa. And two teams set off from England, split up at the island of Madeira. One team headed by Davidson and Cromlin headed for Sobral, a city in northern Brazil, to set up their telescopes, while Eddington and Cottingham went to the small island of Principe, a Portuguese colony just off the coast of West Africa. They made the measurements during the eclipse. On Sobral, they had two telescopes, a 4-inch and a 13-inch telescope, but as often occurs in these eclipse measurements, you cannot control the weather, and there was a cloudy weather. Furthermore, the 13-inch spontaneously changed its focal length during the eclipse, so that data was not used, while the 4-inch telescope gave 7 photographs of the stars near the sun, with 7 stars visible on each photograph. They waited a month to make photographs of the same field of stars when the sun had moved off to a different part of the sky. You must compare the stars with and without the sun to measure the tiny deflections of the images. And then they departed to return to England on July 22nd. On Principe, Eddington had just one telescope. The weather again was bad there, and they managed to get only 2 usable plates, each one having 5 visible stars. For various reasons, they didn't wait to make the comparison photos. They had made those earlier in the year using a telescope in Oxford. They left in mid-June and arrived in Liverpool on July 14th. Now, part of the fairy tale about general relativity is that it was all about Eddington. That was it. But in fact, American astronomers were keen to measure the deflection of light as well. In particular, William Campbell and Heber Curtis of the Lick Observatory in California wanted to measure the deflection of light, and were anxious to actually beat the Brits to getting a test of Einstein's theory. So they analyzed photographic plates from a 1900 eclipse near Augusta, Georgia in the eastern US, and a 1918 eclipse in Washington State in the West. However, the images that they had from those plates were very poor, and they found no unambiguous evidence for Einstein's deflection. In fact, Campbell traveled to England for the summer 1919 meeting of the Royal Astronomical Society and reported that he had failed to detect the deflection of light. Interestingly enough, Astronomer Royal Dyson reported at that meeting that he had received a telegram from Eddington just before Eddington left the island, that Eddington felt that he might have a positive result to report. And of course, they did get a positive result in Sobral from the 4-inch telescope. They got a value for the deflection extrapolated to the limb or the edge of the sun of 1.98 arc seconds. The prediction of general relativity is 1.75. So that was just 10% higher than the GR prediction, but well within the error bars. The Principe result was also in agreement with general relativity with larger error bars because, of course, they had fewer stars to observe. But as I said, there was a lot of skepticism about this result. And even in later years, around 1980, some historians of science criticized Eddington, feeling that he had, because he really thought general relativity was right, that he may have selected the data in a biased way. They questioned why they did not use the 13-inch data and so on. Around the same time, strangely, a reanalysis was done of the plates from Sobral. The Eddington's plates had, for some reason, been destroyed or lost over the years. but the plates at Oxford were still there. And so they reanalyzed both the 4-inch telescope plates and got the same, almost the same result as the people on site had obtained. And even reanalyzed the images from the 13-inch telescope and got a result that was in rough agreement with general relativity, but of course with larger error bars to reflect the added uncertainty because of this spontaneous focal length change. And so the results were in agreement. And our colleague Daniel Kennefick has written a book about this whole episode, and he concluded on balance that Eddington and his colleagues did the best they could with the data they had, and he found no evidence of any kind of bias toward general relativity on Eddington's part. And of course, Eddington made his report of the successful measurements on November 6, 1919, at a joint meeting of the Royal Society of London and the Royal Astronomical Society. And of course, Eddington was a master of self-promotion and publicity, and so he had kind of engineered this whole scene to make the biggest impact on the outside world. And indeed, the philosopher and mathematician Alfred North Whitehead said, "The whole atmosphere was exactly that of a Greek drama. In the background, the picture of Newton to remind us that the greatest of scientific generalizations was now, after more than 2 centuries, to receive its first modification." I mean, you couldn't think of a more dramatic scene to develop. And of course, the next day after Eddington made his huge announcement, the newspapers reported revolution in science, Newtonian ideas overthrown. 2 days later in the New York Times, lights all askew at the heavens, men of science, notice only men of science, no women, of course, in those days, more or less agog over results. Not totally agog, but just more or less agog. Einstein's theory triumphs, and so on. So you get the idea of the feverish nature of the publicity that surrounded this event. And of course, this event made Einstein famous. There are parades in his honor. He's here in Hollywood chatting with the film star Charlie Chaplin. He loved to interact with the press. Here he is in Arizona visiting the Hopi Indians on a big tour of America. And even to some degree, the skepticism of American astronomers began to be damped when Campbell and Trumpler during a 1922 eclipse also got a measurement of the deflection in rough agreement with the 1.75 arcseconds of general relativity. On the other hand, there was a backlash, particularly in Germany, a backlash to Einstein's success and fame. This was the early 1920s now, and the rise of anti-Semitism, Nazi ideology was beginning. And this was accompanied by anti-relativity campaigns promoted by people like Philippe Lenard, who had won the Nobel Prize in 1905. But he was an early supporter of the Nazi ideology, and he denounced Jewish science, such as relativity, based on the fact that Einstein was Jewish. But soon, this decline of general relativity was also aided by a dramatic failure in testing general relativity. In 1907, Einstein had what he later called his happiest thought. This was right after special relativity, and Einstein had this idea that there was an equivalence between what you see in an accelerated frame in empty space and a reference frame in a gravitational field at rest. And this equivalence principle ultimately became the foundation for his development of general relativity, and a very key, even today, a key foundation of all of gravitational theory. And an immediate consequence of this equivalence between acceleration and gravity was the gravitational redshift. A beam of light going down in a gravitational field would have its frequency shifted to higher frequencies, blue shifted, and a ray going upward would be redshifted or shifted to lower frequencies. This was a prediction he could already make in 1907. Well, after the general relativity was published in 1915, the prediction came immediately out of the mathematics of general relativity. And so people set out to test this idea. And indeed, this redshift Einstein felt was the key test of general relativity. It wasn't Mercury's perihelion, which in fact he had used as a filter to reject or keep some of his earlier draft theories before 1915. And it wasn't the deflection of light, which after all was just a doubling of what Newtonian theory would have predicted. This redshift, Einstein felt, was the key test of his theory. And so in 1917, several attempts were made to measure the shift of spectral lines from the sun as they approach the Earth, one by the astronomer Charles St. John, and another by a team of astronomers at the Kodia Canal Observatory here or there in India. But they found no effect. They failed to detect the redshift effect. Some astronomers, some historians of science feel that that hurt Einstein's chances for the 1918 Nobel Prize. And as we know, he didn't win the prize until 1922. And then it was mainly for his work on the photoelectric effect, not for general relativity. For obvious reasons, the empirical foundation was at that time seen to be so weak. A famous attempt was made to measure the redshift using white dwarfs. White dwarfs had been discovered recently and were beginning to be understood. And it was clear that these were stars that were sort of roughly the mass of the sun, half the mass of the sun, but were much more compact than the sun. And so the redshift of light from atoms at their surface would be maybe 100 times bigger than the effect from the sun, and so easier to measure. And it was known that the star called Sirius B, the companion to the dog star Sirius A, the brightest star in the night sky, Sirius B, the companion, was a white dwarf. And so Walter Adams of the Mount Wilson Observatory in California set out to measure the redshift of the light from Sirius B. And Eddington set out to make the prediction from general relativity. The mass of the Sirius B was known from its orbital motion around Sirius A, but you needed a value of the radius. And Eddington figured that he could estimate that by building a model for the white dwarf. So Adams did the spectra, Eddington made the prediction, and in 1925, they announced that they had done the test and it supported general relativity. And once again, big headlines in the newspapers here, July 1925 in the New York Times, right next to a story about a dog patient in a hospital herding a stray pup. Anyway, but within about a year, the whole thing began to fall apart. Astronomers noticed that Adams' spectra were very complex, difficult to interpret, especially because of the presence of scattered light from the much more bright companion, major star, Sirius A. And furthermore, by 1926, it was realized by people like Ralph Fowler at Cambridge and others that Eddington's model for white dwarfs was completely wrong. He was thinking about an extreme star at the extreme end of the main sequence, whereas by 1926, people were realizing that white dwarfs were something new, stars supported by the degeneracy pressure of electrons imposed by this newfangled theory called quantum mechanics. And so the radius relation with mass would be very different from what Eddington used. And so very soon, this supposed test of Einstein's theory was seen to be simply wrong, or at least not believable because it was so deeply flawed. And so by 1950, Einstein himself had to admit that his redshift effect was not yet confirmed. And this was in his mind, key test of the theory. And this was really what John Eisenstadt, a well-known historian of GR, has called the low watermark of general relativity. From the 20s on, very little research was done in the theory, most of it highly mathematical and very abstract and abstruse. And by the 1950s, the field was considered to be in the backwaters of physics. Keep in mind that after the Second World War, the real directions of physics were elsewhere. Atomic physics, nuclear physics, high energy physics, lasers, semiconductors, all the kinds of science and technology that came out of the war work. Those were the main themes of physics, not general relativity. And I'll give two stories to illustrate the attitude of this period around 1960. The first story has to do with a young student who was just getting his bachelor's degree from California Institute of Technology and was on his way to Princeton to do graduate work. This young man was told by a very famous Caltech astronomer, whatever you do when you get to Princeton, do not study general relativity because it will never, ever have anything to do with real physics or astronomy. Luckily for me and many of us, that young student ignored that advice. His name was Kip Thorne. A second example, Richard Feynman, the famous American physicist, attended a GR conference in Jablona, Poland. Jablona is a city near Warsaw. Later, the GR Society would rename this conference GR3, the third in the series, or really the fourth in the series of GR conferences. But Feynman, in attending this conference, wrote back to his wife, because there are no experiments, this field is not an active one. So few of the best men are doing work in it. The result is there are a host of dopes here, and it is not good for my blood pressure. So this was, again, was an attitude about the field at the time. Feynman thought it was not a worthy field to study. And notice he also talked about few of the best men are working on it. Indeed, although there were even a few prominent women at the day, clearly, as in most of physics and science, women dominated. It's a different world today, and maybe even a better world in the future for women. And a common saying of that particular period in time was that GR is a theorist's paradise and an experimentalist's hell. But in the early 1960s, 1961, things began to change. First, because of discoveries by the astronomers. And then during that decade, remarkable discoveries were made. Quasars in 1961, the 3-degree background radiation in 1964, pulsars in 1967, and in 1971, the discovery of the first black hole candidate in the X-ray source Cygnus X1. So these discoveries gave the idea that general relativity might actually begin to play a role in astrophysics. And then the second factor was the development of high precision technology, atomic clocks, lasers, the whole machinery of the space program and the space race that would provide tools to do new experimental tests of general relativity and to make new discoveries. And thirdly, as GR historian Jürgen Rennen and his colleagues have pointed out, was the beginnings of a development of a community of general relativists that began soon after Einstein's death in 1955, partly with the organization of these periodic conferences, GR conferences, of which the Jablona conference was one. And so this beginning of a development of a community of relativists allowed relativists to respond very quickly to this discovery of quasars in 1961. These quasars were very distant, but so bright, so luminous, that no one had the slightest idea what could be the source of such power. And so in 1963, 3 relativists at the University of Texas in Dallas, Ivor Robinson, Alfred Schild, and Engelbert Schucking, decided to organize a conference that would bring together astronomers and astrophysicists and relativists to see if they could figure out what was going on with these quasars. This conference came to be known, that was the first in what came to be known as the Texas Symposia on Relativistic Astrophysics. It was held in the middle of December of 1963. And if you know a bit of your American history, you will recognize this. The conference was opened by Texas Governor John Connally. He greeted the attendees at the conference, but his arm was still in a sling because he was in the car with President John Kennedy during the assassination of Kennedy a month earlier in Dallas. And one of the bullets that passed through Kennedy also struck Connally in the arm. And so he still had a sling from that injury. So you can imagine the supercharged atmosphere at this meeting, both because of the science and because of the tragedy of a few weeks earlier. At this meeting, there were 240 astronomers and astrophysicists and 60 relativists. And I looked at the list of all the people in attendance, and I can say pretty accurately that those 60 represented all the relativists in the world, with the exception of relativists in Eastern Europe and the Soviet Union. This, of course, was still the middle of the Cold War, and those relativists would have been unable to leave to come to this conference. But all the other relativists, this 60 was it. When you think about today's world, it's quite different. And they discussed what could be the source of power for these quasars. Willie Fowler and Fred Hoyle talked about the collapse, gravitational collapse of supermassive stars as providing the energy for the quasars. Tommy Gold of Cornell and his collaborators talked about very dense star clusters, clusters of stars that would undergo gravitational collapse to what they still called the Schwarzschild singularity, and that would be the source. John Wheeler came from Princeton to talk about the collapse of compact objects like neutron stars, probably not a very plausible source, but they had been working on relativistic collapse of these neutron stars. Wheeler, of course, brought a very young PhD student of his called Kip Thorne to that meeting. But it was all about the collapse. There was almost no discussion at this meeting of the black hole itself as the central engine of the energy of quasars. Today, of course, that's the accepted model. It's really the black hole and its gravitational fields and its spin that really provide the energy for the quasars. But in those days, they were focusing on the collapse. A strange paper was delivered at this meeting by a young mathematician from New Zealand based on a phys-rev letter that he had published a few weeks earlier called Gravitational Collapse and Rotation. His name was Roy Kerr. And people who were at that meeting vividly remember the Greek relativist Achilles Papapetro during Kerr's talk, of course, which is all mathematical, killing vectors and symmetries, and it was all, the astronomers were all scratching their heads. They didn't know what the heck this guy was talking about. But Papapetro stood up after the meeting and turned to the audience and said, I think we all should pay close attention to what this young man has done, because I think it could very well be important. And indeed, it was, as we all know. However, not everyone was felt that they were all feeling the love between astronomers and relativists. The astrophysicist Philip Morrison from MIT said he was interested in the idea of bringing these groups together, but he was unpersuaded that it was ever going to mean anything. And the relativist Peter Bergman said he wasn't very optimistic that this was all going to be a fruitful endeavor, this combination of the two. But it was Tommy Gold from Cornell who had the last laugh, I think. During his banquet speech at this Texas symposium, he said, it was, I believe, chiefly Fred Hoyle's genius, which produced the extremely attractive idea that the relativists, with their sophisticated work, were not only magnificent cultural ornaments, but might actually be useful to science. I have a bad delay on my button. Everyone is pleased. The relativists, who feel they are being appreciated, who are suddenly experts in a field they hardly knew existed. The astrophysicists, for having enlarged their domain, their empire, by the annexation of another subject, general relativity. It is all very pleasing, so let us all hope that it is right. What a shame it would be if we had to go and dismiss all the relativists again. Well, this was sort of the beginning of this renaissance, and by the summer of 1969, this relativistic wave was building up, and I was lucky enough to catch it at Caltech. This is the Bridge Physics Laboratory where the relativity group was housed at Caltech in those days. This is not me, by the way. I never graduated beyond body surfing, but I was in the right place at the right time to catch this wave. In the summer of 1969, or the late spring of 69, Kip's group of graduate students was working on all the kinds of subjects you would expect in this emerging field of relativistic astrophysics. Perturbations of black holes and the radiation, the gravitational waves they would emit, questions in gravitational radiation reaction, properties of relativistic stars, relativistic star clusters, and so on. And of course, I was the newest student to join the group. Although I came from Canada, it did not take me very long at all to be a complete convert to the Southern California lifestyle. But at the very time I was being invited by Kip to sit in on his group meetings and to think about joining the group, a stunning announcement was made that possibly sent things topsy-turvy. This is the announcement in PhysRev Letters of June '69 by Joe Weber, who announced that he had detected gravitational waves. Weber had used these large cylinders of aluminum outfitted to detect the vibrations induced by a passing gravitational wave. He had one in Maryland at the university where he was a professor, and another outside Chicago at Argonne National Lab. And he was seeing simultaneous excitations of these bars, as many as sometimes 2 to 3 per day, many per week, at an intensity that was so large that nobody could understand what could be the source of these gravitational waves if they were waves. In today's language, we talk about LIGO detecting a strain of H of around 10 to the minus 22. You can work backwards and realize that the effective H Weber was detecting was about 10 to the minus 15 million to 10 million times bigger than what we are actually detecting today. What could be the source of these gravitational waves? Nobody could have the slightest idea, but Kip started to worry, well, could Einstein be wrong? Could we simply be using the wrong theory of gravity to calculate these gravitational waves? And so he looked at me, the newest student in his group, and said, Cliff, I want you to find out how right general relativity is. So I set about that summer of 1969, this was the end of my first year at Caltech, to find out. So I studied the literature going all the way back to the 1920s, read papers, review articles, and so on. I learned that, for example, the famous Outwash experiment of the turn of the 20th century had been improved by a factor of 100. This is the equal free fall or equal acceleration of bodies of different material. Dickey had improved that limit by about a factor of 100 in 1964 at his lab in Princeton. The gravitational redshift had actually finally been measured, not with astronomy, but with a laboratory experiment measuring the shift of frequency of gamma rays from isotopes of iron, measured to about 10% to 1% by Robert Pound and his student Glenn Rebka at Harvard. The solar redshift had finally been measured by James Brault, a student in Dickey's group, to about 5%. Mercury's perihelion advance, another important test of general relativity, was only known to about 20% at that time. Not very good at all. And the only way to measure the reflection of light still was through solar eclipses. And as recently as 1952, that effect was known only to about 10%. Meanwhile, Dickey and his graduate student Carl Brands had invented an alternative theory of gravity that was completely viable, theoretically robust, and could satisfy all existing experiments with a value of the scalar tensor coupling constant around 7. And so it was a perfectly viable alternative to general relativity. So as weak as this situation was, I also learned in my reading that help may be on the way. The newly developed technique of radar ranging, developed just around 1960, with bouncing radar signals off the surfaces of planets and receiving the echo, promised to improve the accuracy of our knowledge of planetary motions quite dramatically. Leonard Schiff at Stanford University had shown that the rotation of the Earth would induce a precession in a gyroscope and proposed measuring this effect or testing this effect by putting gyroscopes into orbit around the Earth. Radio astronomer Erwin Shapiro discovered what he called the fourth test of general relativity in 1964. This was a theoretical discovery. He worked it out that there would be a delay in the propagation of a radar beam on its way, say, to a planet or a spacecraft and back to the Earth. And a few years later, Shapiro again, he proposed using radio interferometry. Again, radio astronomy was developing rapidly. He proposed using radio interferometry to measure the bending of light, which would then no longer need to rely on solar eclipses. And meanwhile, NASA was in the midst of the Apollo program and was considering putting a laser retro reflector on the surface of the moon at the urgings of Dickey and others to then improve our knowledge of the lunar orbit by bouncing laser beams off the specially designed set of reflectors. So the beginnings of a new effort in different areas of experimental relativity were starting. And in fact, Shapiro, with his team, went out and measured the time delay by bouncing radar beams off Mercury and Venus in 1968. And so Kip sent me up to JPL to talk to people there. JPL was in charge of the spacecraft Mariners 6 and 7, which had been launched to study Mars, and then would then go around behind the sun after the encounter with Mars, and they were planning to measure the Shapiro, what we call today, the Shapiro time delay. So I went up there to talk to the people in charge of that program to find out how well they thought they could do in measuring the time delay. But my big discovery that summer was this. I discovered 3 remarkable papers written by Ken Nordtvedt Jr., a young relativist at Montana State University in Montana. Nordtvedt had taken the post-Newtonian metric of general relativity, the first post-Newtonian corrections to Newtonian theory, and had stuck in place of the numerical values an arbitrary parameter in front of each term in that metric. He then asked what would be the acceleration. This was a metric for point masses, just a collection, a cloud of point masses. And he asked the question, what would happen if what would be the acceleration of a self-bound, a self-gravitating cloud of such masses in the external field of some other mass? And he found that that acceleration would not be the same as the acceleration of a single particle in that field, depending on the theory of gravity. In general relativity, the acceleration was exactly the same. There's a big cancellation of effects. But in alternative theories of gravity, including the Brand-Sticky theory, the acceleration would depend on the internal gravitational binding energy of the body. This is a kind of violation of the equivalence principle for massive self-gravitating bodies. And Nordtvedt went on to propose testing this idea using lunar laser ranging by measuring whether or not the Earth and the Moon were falling with the same acceleration toward the sun. So this was quite a remarkable series of papers by Ken. But I realized in reading those papers that I could generalize what he had done in a significant way. I had, in my GR course with Kip, had studied very carefully Chandrasekhar's work on post-Newtonian hydrodynamics, where you treat the bodies as fluids with internal pressure, an equation of state, internal energy, much more realistic than a cloud of point masses. And so I could generalize Nordtvedt's framework to perfect fluids. And so with Kip, we called this the PPN, or parameterized post-Newtonian formalism. But the true origin of the PPN framework that people are familiar with today came in 1971 in Bozeman, Montana, where Nordtvedt had organized a summer workshop on tests of GR. And one attendee at that workshop was a student of Kip's called Sandor Kovac, who would later leave general relativity and become a very noted cardiologist at the Washington University School of Medicine. But at that time, Ken and I had very different versions of our formalism. He used point masses, I used fluids. He had 8 PPN parameters, I had 10. We had different signatures for the metric, our conventions were different, blah, blah, blah. And Sandor grabbed us together and said, I'm going to lock you in a room and throw away the key until you talk to each other and merge your 2 formalisms into a single unified formalism that everyone can use. It'll be much more useful. And in fact, we did. Sandor nagged us so incessantly that we were forced to get together and produce what is today the canonical PPN framework with the parameters gamma and beta, which are actually date all the way back to Eddington, but with other parameters that describe different effects that you could get depending on the theory of gravity you're working on. And so this is the framework that we all know and love today. And Ken and I put things together, and there was for everyone to use. And in some sense, the 1970s were the golden age of testing general relativity. And I'll just sort of run through a list of the kinds of things that happened during that decade of the 70s. The Shapiro delay, which measures the parameter gamma, measured in the dates here are the publication dates: 1975 with Mariner 6 and 7, 1978 with Mariner 9, culminating in the measurements using the Viking landers and orbiters around Mars to an accuracy of 0.1% in terms of measuring gamma. That result held until 2003, when it was improved by about a factor of 100 using data from the Cassini spacecraft on its way to Saturn. The gravitational redshift effect was measured by putting clocks on aircraft and flying around the world on planes. But the best test for a long time was a project called Gravity Probe A, which put a hydrogen maser atomic clock on a rocket and compared its rate with an identical clock on the ground. And here's a picture of Bob Vassaux, the pioneer of hydrogen maser atomic clocks, and his colleague Marty Levine holding one of their hydrogen maser clocks, lifting it off the floor. This would be installed on a Scout rocket. Mercury's, because of this planetary radar technique, dramatic improvements were made in Mercury's perihelion effect, which measures gamma and beta in a combination, down to a level of about 0.5%. And soon after Neil Armstrong deposited one of these corner reflectors on the moon, astronomers could then start to detect the laser beams bounce back to the Earth and measure through timing the distance between the Earth and the moon. And over the many years, they searched for the Nordtvedt effect and found zero effect in agreement with general relativity at the level of about 0.01 in terms of these parameters. So it was a very active period for testing general relativity. This all culminated with a fantastic announcement having to do with gravitational waves. In September 1974, I was a brand new assistant professor, taking on my first faculty position at Stanford University, sitting in my office, kind of getting settled in, and my colleague Bob Wagner burst into my office holding a telegram. Now, some of the young students here at the workshop may not even know what a telegram is, but this was a special telegram called an IAU telegram. The International Astronomical Union in those days would announce new discoveries in astronomy by sending the initial details of the discovery in a telegram that would be circulated to all the observatories, universities, and institutes around the world. The service still exists today, but of course it's all done on the internet, not with physical printed telegrams that you receive on a teletype machine. But Bob, at that time a noted cosmologist, but who had turned his attention lately to general relativity, Bob was one of the most enthusiastic scientists I have ever met. And he burst into my office with this telegram saying, "Cliff, they've just discovered a binary pulsar. Whatever you're working on, drop it. We've got to work on this new thing." He was referring, of course, to the famous binary pulsar of Joe Taylor and Russell Hulse, a new pulsar that Hulse had discovered working at our beloved Arecibo telescope, which is now no more. A pulsar that was so strange that its pulse period changed in dramatic fashion, but soon recognized as being the result of orbital motion of this pulsar around a companion star. The effects he was seeing were just simply the Doppler shifts of its apparent pulse period. So Taylor and Hulse announced they had detected this, and for the next 10 years or so, many of us worked diligently on trying to understand the implications for general relativity of this great new discovery. And of course, the capstone of this all was in 1978, when at the Texas Symposium, the 9th Texas Symposium, this time in Munich, Germany, Taylor announced that he had measured the rate of decrease of the orbital period that would be a consequence of gravitational wave energy loss. And what I plotted here is the cumulative shift in periastron time. It's like the double time integral of the rate of change dp dt. So it's a decreasing parabola from 1975-74, the discovery, until 2008. Taylor at the Texas Symposium reported on this of the day resulted in 1993 with the award of the Nobel Prize in Physics to Hulse and Taylor, the first Nobel Prize ever to be awarded for work that really strictly has to do with general relativity. And of course, a few weeks after the big announcement of the prize, I received a fat envelope from the Nobel Foundation inviting me and my wife to attend the ceremonies as the guest of the foundation to help honor Halston Taylor. So this is quite a fantastic moment for me and my wife. And I show this picture of me at this at the Nobel Prize ceremonies just to prove that I do know how to dress properly every once in a while. And now I want to turn to my last topic, this synergy between theory and experiment. And I remind you that 1974, the discovery of the binary pulsar was also the year of the first calculation in numerical relativity, here of the head-on collision of two equal mass black holes carried out by Larry Smarr and colleagues based on earlier work by Susan Hahn and Richard Lindquist. But the discovery of the binary pulsar soon was followed by a paper by Jürgen Ehlers and collaborators that was a very thorough criticism of the foundations of everything we know about the equations of motion and radiation reaction and gravitational waves in general relativity. They argued that the so-called quadrupole formula that we use to calculate things like energy loss had really no basis in fact as a prediction of general relativity as it was understood then. This paper annoyed many of us in the field. It annoyed us in the sense that when your mother tells you to eat your vegetables because they're good for you, it really makes you angry. It makes you annoyed. You know your mother is correct, that vegetables are good for you, but you do not want your mother telling you that to eat your vegetables. We knew that Ehlers et al. Were correct. They told us that all the calculations done to that point had assumed that the bodies were point masses, delta functions. Well, point masses cannot exist in general relativity. They pointed out that people used a multiple approximation to describe the radiation, quadrupole, octupole radiation. Well, in electrodynamics, that's fine because the charges are confined to finite regions. But in general relativity, gravity itself produces gravity. So the source of these multiples actually extends over all space. So you have to integrate overall space to calculate things like the quadrupole formula. But you'll reach a point where some of these multiple integrals will diverge. They also pointed out that in the binary pulsar, we calculate the energy flux at infinity and assume that the loss of energy in the orbit equals the energy loss to infinity, called energy balance. It's a reasonable assumption, but Ehlers et al. Pointed out there's no actual proof that that is correct. And they had a laundry list of things like this that really, they were really right. We had done many things that violated these kinds of sensible things, so around the same time, for example, with Bob Wagner, based on work he had done with Ruben Epstein, Wagner and I calculated the first post-Newtonian corrections to the quadrupole formula. And I can assure you that we swept many, many divergences under the rug in that calculation. So we were as guilty as the people Ehlers was criticizing. So this paper was very influential because it really induced a lot of us to begin re-examining these foundations, going back to square one in all these calculations of the equations of motion and gravitational radiation reaction and gravitational waves. And so for the next 10 or 12 years, many of us spent a lot of time trying to build up the theoretical foundation of this whole era, simply because we wanted to have robust calculations to agree with, for example, the ultimate measurement of the damping of the binary pulsar orbit. And Taylor announced the observable effect, but you had to be sure that the theoretical prediction was correct as well if you were to believe that this really was a verification of general relativity. And so this is really an example of the beginnings of this kind of synergy between theory and experiment. The observers, the astronomers were telling the theorists that you had to get your act together to develop the calculations and be really confident in them if you are to agree and say that you agree with the experiments. And this was raised to, the stakes were raised even higher in 1990 with the development of laser interferometric gravitational wave detectors. The people who were starting to begin designing and constructing the LIGO and Virgo gravitational wave detectors were telling us that if we're going to detect gravitational waves from in-spiraling binary systems like neutron stars and black holes, and extract science from that gravitational wave data, we would need not just the quadrupole formula, but we would need these formulas developed to very high orders in the post-Newtonian expansion. So this really forced a lot of us to go to these higher orders, while at the same time paying attention to all the various issues that Ehlers and colleagues had raised about having these calculations done robustly without divergences and without all the other flaws of the earlier methods. So many methods were developed in response to really these requirements for the gravitational wave detectors. The post-Minkowskian method of Blanchet and Damour and Cy Iyer and their colleagues, the direct integration of the relaxed Einstein equations method of my group then at Washington University in St. Louis. Gerhard Schaefer and his Jena group had a method. Toshi Futamase in Japan. Effective field theory developed by importing methods from particle physics. The effective one-body approach of Damour and Bonanno, and so on. Many methods developed to address higher order, more accurate gravitational waveform predictions for gravitational wave detection. And a lot of these methods were applied to developing predictions in alternative theories of gravity, such as scalar tensor theory, massive graviton theories, and so on, so that we could even test alternative theories with gravitational wave data. In 1990, ironically, I was giving a talk reviewing many of these developments at a Yukawa seminar in Kyoto, Japan, and Jürgen Ehlers was in the audience. And I think either somebody in the audience or I cannot remember, asked Jürgen point blank, Jürgen, are you now happy with these new developments in understanding the equations of motion and gravitational waves? And Jürgen sort of went, well, I wasn't so sure. I'd known Jürgen for many years at that point. He said, well, maybe that he admitted that he was happier than he was. Well, as I say, I've known Jürgen for a long time. For him to say that he was happier than he was, to me, was a strong stamp of approval on all the work that we had done. And of course, to top everything off was the binary black hole breakthrough in numerical relativity that allowed us to get gravitational waveform predictions for the actual merger process. Many of you don't realize that around 1990 time, people at LIGO, Kip and others were becoming actually rather desperate that they would not have theoretical predictions of sufficient accuracy by the time LIGO actually detected waves. And they felt that that would be a disaster if they detected waves and could not confirm the detection because they did not have accurate enough predictions. So this really was a case of the strong synergy between theory and experiment. The experimentalists were forcing us theorists to do work, and with lots of back and forth as to what had to be done to extract the most science from gravitational waves. So in this talk, I've sort of tried to give you an idea of how the fairy tale version of general relativity is not correct, as the situation is much more complicated. General relativity fell into the backwaters of science, but then in the 60s began this great renaissance, which I was privileged to participate to some degree. But the important thing that is somewhat new to this field is this synergy between theory and experiment. And I'll just close with what I think is a quintessential example of this synergy. At that GR3 meeting in Jablona, Poland, there was one talk about experimental gravity given by Vitaly Ginzburg. At GR22, the 22nd version of those triennial meetings in Valencia in 2019, 10 of the 18 plenary talks were all about experiment or observation. There were talks about LIGO and its detections and discoveries, talks about developments in pulsar timing arrays and LISA, talks about imaging of black holes and studying stars at our own galactic center, orbiting Sagittarius H star, talks about observational cosmology and precision cosmology, talks about analog gravity, studying analogs of things like Hawking radiation in normal laboratory experiments with things like Bose-Einstein condensates. And capped by a talk, it was actually the first talk of that meeting, on the 100th anniversary of Eddington's famous experiment that in some ways started the fairy tale version of Einstein's theory, given as it happened by me. So I want to thank you very much for giving me the chance to talk a little bit about the history of our subject, and I'm happy to take questions if that's allowed. Thank you.
Thank you, Professor Will, for such a wonderful lecture. The floor is open for questions. While I ask the questions that are already there in the chat, what I would urge the participants, they can log their questions in the Q&A using the Q&A button. So I'll first read the questions that are already there in the Q&A section, and then I'll come to the raised hands. So let me start from the top. So there is the first question, that is, how far are we from the quantum theory and GR reconciliation?
It's a very easy question to answer. The answer is, I don't know. It's a very difficult problem, and lots of people are working on this reconciliation between GR and quantum theory, and it's not something I follow carefully. And one aspect of this whole reconciliation that it's a reason why I don't follow closely is that I really follow the issue of experiment. And unfortunately, in quantum, things like quantum gravity, it's very difficult to see realistic experiments that could tell you whether you're on the right track toward a full quantum theory of gravity. And so I'm pretty agnostic about that whole field. I follow it at some very low level, but I really don't know what the future brings for that question.
Thank you. The next question is, what is a gravitational wave?
Well, if you have about 6 hours, I could tell you. But roughly speaking, it's a ripple in the very fabric of space-time. That's a key aspect of general relativity, that gravity is really an aspect of the geometry of space-time. And you can actually see the waves behind me. This is kind of an artist's rendition, of course, of waves being emitted by two black holes orbiting each other, getting closer and closer, faster and faster. So the waves get stronger and stronger. They ripple outwards, and then they can be detected because they cause, say, masses, freely moving masses, to go back and forth relative to each other. And you can measure that variation in distance using, say, beams of light, laser beams, which is exactly how the LIGO gravitational wave detectors work on Earth. And what's pictured behind me is the space antenna LISA that's planned for launch in the early 2030s.
Thank you. So the next question is, what happens if all water vanishes from Earth? Sorry, there's messages coming in, so I'm losing the track. So what happens if all the water vanishes from Earth? Its effect Earth gravity.
It seems like a silly question, but actually, in some sense, it's not. There's our spacecraft orbiting the Earth called GRACE, two spacecraft that measure the gravitational field of the Earth with unbelievably high precision. And they can measure the changes in Earth. This has really very little to do with general relativity. It's all just Newtonian. But they can measure changes in the Earth's gravitational field caused by seasonal changes of the amount of water in the Amazon River Basin or in the Ganges River Basin. So the distribution of mass on the Earth, let's say the seasonal distribution because of rising and falling water levels, can be measured in terms of its effect on Earth's gravity. So this is not a relativistic question, but it's certain. I know a bit about GRACE, so it's just amazing you can measure Earth's gravity with such incredible precision.
Okay, I hope that is clear now. So what lies ahead? What comes after LISA?
Well, let's get to LISA before we worry about what comes after LISA. I mean, LISA is really, well, there are two aspects. I mean, there's LIGO and the ground-based detectors, and people are already planning for the next generation of ground-based interferometers beyond LIGO. There's ET, Einstein Telescope in Europe, there's Voyager in the USA, and various new interferometers on Earth in America. But this is, like thinking 10 to 15 years ahead. LISA, of course, has been in the works for almost 20 years, has now entered phase B, which in space terms is a crucial development phase for a big space project like this, and it will be launched in 2034. I think most people in the field are just worried about getting LISA developed and launched and off the ground, and we'll worry about the next, what comes after that, maybe a little bit later once we see how LISA is going. But I should also mention pulsar timing arrays is another way to detect gravitational waves at the very, very low frequency end of the gravitational wave spectrum, sort of in the nanohertz regime, where you could see gravitational waves from supermassive black holes, but possibly gravitational waves related to the very early universe and so on. But the PTAs are things that we hope will start to succeed detecting waves in just the coming few years.
Thanks. Does dark energy and dark matter has something to do with relativity?
It depends on whom you ask. So these two phenomena, dark matter is believed to be, by most, I'd say the majority of people, some form of elementary particle that permeates the universe that's really responsible because of its gravitational influence on for the evolution of galaxies and the structure of the cosmic background radiation. The problem is that we have not yet detected the particle that is supposedly responsible for this. Dark energy is the phenomenon that is responsible for the accelerated expansion of the universe. The observation recently that the universe's expansion is proceeding faster and faster with time rather than slowing down as you would expect in pure general relativity. So it relates to general relativity in that some people are wondering whether or not we need to modify general relativity at these kinds of very large scales, from galaxies out to the scale of the universe as a whole, to explain the observations that imply dark matter and dark energy. The question of dark energy, and this is my personal view, the dark energy is easily explained by just bringing back the famous cosmological constant that Einstein introduced around 1918 to explain why the universe was static. He had to withdraw that when the universe was seen to be expanding. But now if you bring it back with a rather different value, you can explain or account for the accelerated expansion of the universe quite simply. It's a sort of a minimal effect, a change in GR that would account for that accelerated expansion.
Okay. What are the latest research topics in GRB research for PhD students?
Well, I think the question talked about gamma ray bursts. That's certainly not my field at all, but the latest topics, and I'll only talk about things related to GR and astrophysics. Of course, there's the whole quantum gravity side. That's a separate topic. But the kinds of interesting topics these days really involve the interface between GR and astrophysics. Where do supermassive black holes come from? Can we test general relativity using these kinds of supermassive black holes, either by imaging or studying gas and stars orbiting around them? What more can we learn from the gravitational wave detections? New tests of general relativity have just been published by the LIGO-Virgo collaboration. So there's lots of research to be done on understanding where these binary black holes come from, learning more accurately, getting more accurate predictions from general relativity for the gravitational wave signals they emit, and so on. So in my view, just this narrow area of gravitational waves, black holes, astrophysics is rich with problems for young students.
Okay. The next question is
Chandra, I noticed
yeah.
Sanjeev has a question. He has raised his hand. Maybe you can request him to ask.
Okay, Sriram, so let me just
I can, yeah, Sanjeev, you can proceed with your question.
Okay, thanks.
yeah.
I just wanted to ask, did you think that Roger Penrose played a big role with bringing in spinors and anything, spinor mathematical formalism into general relativity in the 60s, and also the singularity theorems with differential topology and so on. And the Wilson equation, which also led to these theorems.
Oh, I mean, the work that Roger did on all these things, as you mentioned, have been absolutely essential to our theoretical understanding of black holes, of singularities in general relativity, and so on. So they played quite a critical role in the development of the field. Yeah. So yeah, there's no question in my mind. Now, Roger lately has delved into cosmology and has made some rather unusual predictions about what you might measure with the cosmic background radiation, but that's something I haven't really followed in much detail. Okay. But I have to say, I was very happy with the Nobel Prize of that year when Roger won it for that work, and Andrew Ghez and Reinhard Genzel for their work on the galactic center black hole. I mean, two amazing aspects of understanding black holes.
Yes.
Thank you, Sanjeev, for the question. First of all, there are many questions. Maybe I will select a few of them. There is a question asking, how can we determine there is a graviton?
Well, again, this is a question in terms of quantum gravity. The problem is, unlike photons, which we can now see individually or detect individually because of their quantum nature, gravitons are unbelievably weak. The effect of a single graviton, you name something that's the smallest effect you could imagine, and the effect of a single graviton is unbelievably smaller than that. You cannot imagine how weak a single graviton is. You think about the gravitational waves emitted by the sources that LIGO detects. That signal arrives at LIGO and makes those mirrors move by a fraction of a picometer relative to each other. You think that is unbelievably weak. Well, that signal has trillions, quadrillions, what are illions of gravitons passing through the Earth. Enormous flux of gravitons are passing through the Earth just to make those mirrors move by a picometer. Again, gravity is so weak compared to all the other interactions, it's factored in some sense 10 to the 33 times weaker, that I cannot see any way we will ever detect the effect of a single graviton by any sort of realistic means or realistic budget that you might want to spend.
Thank you, Professor Bill. There is another question from Vikram G. Chandra, which asks, can you share your opinion on current alternatives/modifications to GR like MON?
Yeah, so I'll say right from the outset that I'm a firm believer that general relativity is correct. So I'll just full disclosure. However, it's important to consider alternative theories because you need to know what the alternative possibilities are so that you can understand the extent to which GR is correct. And of course, it's entirely possible that we might have to modify GR, especially maybe on cosmological scales. So currently, a lot of the alternative theories that are being studied now are theories that are designed to agree with general relativity on all the usual things, the solar system, gravitational waves, binary pulsars, near small scale phenomena, but then are designed to possibly explain the accelerated expansion of the universe, which general relativity cannot explain without having the cosmological constant, or to try to explain these rotation curves of galaxies and other observed phenomena that are the evidence for dark matter, which this MOND model has been developed to explain without dark matter. And so there's a lot of development. Some of these theories have been killed recently by the observation that the speed of gravitational waves and the speed of light are the same to about a part in 10 to the 15. This is from the binary neutron star detection, both in gamma rays and in gravitational waves. That turned out to wipe out about half a dozen theories. MOND itself, I think, is not well favored these days, just because their observations it has difficulty explaining, and even most of the proponents of MOND, the way I understand it, feel that the model they have to have some dark matter if they really want to explain all the observations. It has to be a combination of MOND and some kind of dark matter to explain everything. So it's but the great thing about it is there are observations that you can use to test a lot of these ideas.
Thank you. Maybe we can take a couple of more questions, Professor Will. Is that okay with you?
Yep, I'm game.
Okay, all right. So Pranav Kassetti asks, is it possible we will measure gravitational waves from unexpected sources? Considering how weak the signals are, how can we see something if we don't have a template for it?
Well, in fact, you don't, I mean, I know the templates are used to detect and, these theoretical predictions. However, it's maybe not so well known that the very first detection, 1409-15 or 1509-14, September 14, 2015, that very first detection was detected not using a template. It was detected by a software called coherent wavebursts that use wavelets to detect signals of a certain set of characteristics and does not rely on theoretical predictions of general relativity. Very shortly after that detection, it was also detected by the group that uses templates. So there are ways to detect gravitational waves that don't rely on specific theoretical templates of general relativity. So they're very useful for certain kinds of detections. But and this has been a big deal with LIGO, trying to develop methods that can detect signals that are completely unexpected, have a shape that we had no idea the waves would come in that form. But even already there have been surprising detections. And one of the key ones is that the binary black hole mergers have all mostly involved black holes much more massive than anyone ever expected. Instead of the 5 to 10 solar masses that we see, for example, in X-ray sources, X-ray binaries and so on, these were 30, 40, 50 solar masses. And that has opened up a whole new field of research because it's not so easy to find formation channels that can produce binary black holes with these kinds of high masses, 50, 60 solar masses. So these were not new objects, but they were objects in a mass range that no one ever expected. And so even at that level, we're finding unexpected things that are challenging theorists to understand.
Another question concerning numbers. How big are displacement between two freely falling masses very, very close to a binary black hole merger? Could an observer be displaced by a GW if this observer is very close to such a merge?
You could, but it's still very small. If you put yourself just, say, one wavelength of the wave, so you have to be in the wave zone, so you're detecting waves, not just the various near gravitational fields of the two black holes. I'd have to sit down and do the calculation, but even then, it's still very weak. You would not, for example, you could not feel yourself being stretched and squeezed the way you feel at a detector. I believe that those forces, even a few wavelengths away, are so small, you couldn't feel them. But it's not hard to put in the numbers and work it out. So I encourage, there's a problem for students, take a binary black hole merger, near merger, and calculate the tidal forces about 5 wavelengths away from it. So you're really seeing the waves and see how those forces compare to, say, the strength, tensile strength of your skull. I think it's still pretty small.
Does every black hole have a singularity?
As far as we know, of course, since the singularities are all inside the event horizon, we can never get information out to find out. So general relativity predicts for sure that every black hole has a singularity inside. However, people who work on quantum gravity hope that they can find a way to avoid having a singularity inside the black hole by some kind of quantum, effect that very, very short distances, perhaps quantum gravity comes in and it prevents an actual singularity. But as long as the black hole is a normal black hole, we couldn't tell the difference.
There is a question which asks, in the extreme environment near the galactic center, black hole Sagittarius A, do you think there will be any deviation from GR from the current theoretical model and observations?
Well, I mean, I certainly hope not. I hope general relativity remains correct. But there are some uncertainties. I mean, the gravitational redshift of the light from this star S2, which is the one that has completed about 1.5 orbits around the black hole, when it went through its periapse, the closest approach to the black hole, astronomers, both in the two groups, measured the gravitational redshift of the light from that star induced by the black hole, and it agreed with general relativity to about, I think, 10%. The group in Germany that studies the black hole says that they've measured the peri-center advance, the analog of Mercury's perihelion advance of that orbit. And so far, general relativity holds up. But on the other hand, we don't know much about what lies between these stars and the black holes. Some people feel that there might be a spike of dark matter distribution close to the black hole, which would be additional mass. And if it's big enough, that would affect the orbits of the stars. Wouldn't be a violation of general relativity, but it would appear as some deviation. And so you might be finding evidence of a dark matter distribution that peaks just outside the black hole. There could be a companion black hole. We see lots of evidence of galaxies with binary supermassive black holes in them, or a big black hole and an intermediate mass black hole. In fact, in my own work, I've been collaborating with the group of Andy Reguez at UCLA and Smadar O's, studying whether or not we can place limits on such a intermediate mass companion black hole by using the data on these orbiting stars.
The next question is it possible to cancel gravitational waves? If yes, how?
Well, no, no. One of the things that differs between gravitational waves and electromagnetic waves is that you cannot shield them. You can cancel electromagnetism, right? You can reduce the magnetic field in a surrounding. This is done in NMR laboratories all the time. You build a shield of conducting material that can cancel the external magnetic fields. You can shield from electromagnetic radiation simply by reflecting it away. You can't do it for gravity simply because, unlike electromagnetism, gravity is always attractive. There are no negative charges in gravity. Everything is positive, everything attracts, and so there's no way to shield the gravitational waves. People have looked at this actually, and it's just, there's can't be done.
Abhishek asks, is it possible to detect gravity waves from 3 black hole mergers? Is it possible to calculate the solution of the 3-body problem using GR?
Well, in certain contexts, sure. You can't solve the 3-body problem, even in Newtonian theory, exactly. There's no exact solution, but there are well-known and very robust approximate methods for studying the 3-body problem, especially when 2 of the bodies are close to each other and the 3rd body is more distant. It's called the restricted 3-body problem, or the hierarchical 3-body problem, rather. So there are ways to do it. And of course, on a computer, you can solve the 3-body problem to very high accuracy. And indeed, people in gravitational waves are thinking very seriously about these kinds of questions, not just not just gravitational waves from binary systems, but gravitational waves from three-body systems or binary systems that are strongly perturbed by a third body, and so on. So this is a very active field, three-body gravitational waves.
Thank you, Subal. There is a sort of personal question. What was your experience on working with Professor Chandrasekhar back in the days as your postdoc? Can you share it in brief?
Well, I mean, one of the things, I learned a lot from Chandra, and Chandra was sort of a great mentor, and just one of the things I really liked about, well, several things I liked about Chandra. One, that he really liked interacting with young people. I mean, many of you have seen pictures of Chandra. He was always well dressed with his silk suit and very formal, very Cambridge type guy. You think he's so unapproachable and so on. But every so often he would invite me to lunch with him at the faculty club. And in those days, this was the early 1970s, my hair was like this down to here. I was a total hippie. I had, bell-bottom jeans and tank tops. I looked like a hippie because we were all hippies in the early 1970s. Didn't bother him one bit. He had his silk suit. We walked down to the faculty club. We'd have lunch, chat. Later on, when I was at Washington University, he came to give a distinguished lecture that we have called the Feinberg Lecture, just like this lecture. And he told me, Clifford, when I come, I want to stay an extra day and I want to meet all the students in your group. And he came, we spent the whole afternoon, all my students gave little short presentations about what they were working on, and he chatted with them, and he taught them. He just liked interacting with young people. I thought that was so great about him. But I also learned I learned from him about doing very detailed, meticulous calculations, being extremely careful. It's the kind of work he did, and it's the kind of work I do. So I learned a lot about how to do those calculations. Of course, he didn't have the advantage of Maple or Mathematica in those days. Today we have help in doing these calculations. And then finally, I learned from him a real sense of appreciation for history of our subject. He told me lots of stories. He told me lots of stories about Eddington because, of course, as we all know, he had strong interactions, both positive and negative, with Eddington during his years at Cambridge in the 30s. And so he had lots of stories about the astronomers he met, his experience as editor of Astrophysical Journal for many decades. So I learned how to like history of the subject from him. So it was a great 2 years that I spent at Chicago in his group.
There are a couple of people who have raised their hands. Maybe we'll take one question from them. Professor, Sanjay, can you unmute and ask your question? Okay, Sanjay, we are not able to hear you.
Now,
yeah, can you ask your question? There is a lot of disturbance.
now am I audible, sir?
Yes, go ahead, please, Sanjay.
Sir, just I would like to know. Just I'm working also the professional physics in one engineering college in Greater Noida, UP, and I'm teaching physics since last 15 years. Is it possible to break the theory of relativity, or how maybe what are the technological changes after breaking the theory of relativity?
Okay.
So I didn't quite understand.
I believe, is there, do you foresee violation of special relativity or general relativity? I believe that is the question.
Well, obviously, it's, there's I think the phrase attributed to Niels Bohr, it's very difficult to predict, especially about the future. That was a joke, by the way. Personally, I don't. With the one exception that we may have to modify it to address these kinds of cosmological questions. But so far, there's no evidence in violation of special relativity and no evidence in violation of general relativity. Every single experiment has supported both of these models or theories. And there's simply nothing so far that violates either one. And the remaining kind of issues like the acceleration of the universe and the question of dark matter the nominal solution is add a cosmological constant to general relativity, which is a pretty minimal change, and just actual elementary particle basis for dark matter. It would be nice if they would detect the particle and we'd then know, but so far that hasn't happened.
Thank you, Professor Will, for your wonderful talk and answering all the questions. I will just hand over back to my colleague, Professor Chandrakant Mishra, for the closing remarks. Chandra, over to you.
Thanks, Sriram. Yeah, I think we were able to address most of the questions. There are so many remaining other questions also, but I think this is all the time we have for these things. Right. I think this brings to the end of the second lecture, second Chandrasekhar lecture. Thank you, Professor Will, for accepting our request and giving this wonderful lecture. And thank you, all the participants, for joining us this late in the evening. I think we can stop recordings. Thank you, everyone.
Okay, thank you.
Thank you, Professor Will, for joining us and giving this talk. Appreciate it. Thank you.